Hello everyone, this is the first class of economic statistics. Welcome to the course. The first chapter in any introductory statistics would be about probability. So that is the basis of any statistics. So before going into the probability chapter, let me preview what you're going to do throughout this semester. So there are 12 chapters, and the first 4 chapters can be categorized as one part called the descriptive statistics. Basically, we are going to learn basic methods to describe data. And the second part is 5, 6, 7, and these chapters talk about distribution models. So when you say a model, that means you make assumptions and simplify things and explain the phenomena and then study the properties based on the simplifying assumptions. Okay, so we are going to learn binomial distribution, normal distribution, some very basic distribution families in the second part. And in the third part is about inferential statistics. Literally, it is about inference. So in some sense, that is the ultimate goal of statistics. Like we are going to learn estimation methods, and also we learn hypothesis tests. You may have heard about these things, and that's actually the key essential techniques you have to learn in statistics. And finally, chapter 11 and 12 will be on linear regression model. So linear regression is a kind of it's a model that applies all these like distributions and inference techniques and simplify that into a linear regression model. And this is actually the goal of this course. The reason why economic statistics is required for economics major is because you need to know the linear regression to learn other like courses like labor economics, international trade, industrial organization, financial economics. All these subfields use data, and the workhorse model is the linear regression model. 95% of, say, empirical work in economics is based on some kind of or some variation of linear regression model. So in the end, after finishing this course, you have to understand what is the basic idea of linear regression model. So that if say in another course, if you learn say labor economics or say finance economics, if you hear that we are going to do a regression, then you should be able to understand what it means. That's the purpose of this course. And especially for this year, this semester, and let me briefly describe my situation. So some of you may know, this is the second year we are doing, we do this on Brightspace. Until 2022, we had a different platform. So actually last year I had to move all the materials from Blackboard, the previous platform, to Brightspace. That took me a lot of time, and especially as an online course, that's very there are a lot of materials, like especially online quizzes. So still a lot of things are not ideal. They exist. I taught this course last year, but I had to update a lot of things I realized last year. So this year my main focus is to update the online quizzes. So sometimes I may be okay, I promise I'll be on time every week. So we are going into chapter 1. So the first part is about descriptive statistics. And as I said, you are going to learn how to describe data and mathematically how to characterize randomness, right? pretty simple because there are only two major ways, fundamental ways to describe data. One is probability, the other is average, and their variations, of course. But in general, roughly speaking, even in advanced statistics, basically the underlying techniques are either probability or average, some kind of applications of them, right? So in the first two chapters, we are going to study probability, and in the following two chapters, we are going to study averages and their relatives. Okay, so these are relevant chapters from different textbooks. So my recommend. By the way, you are not required to have a textbook, but in case you have one, maybe I guess it's one of these. That these are what I have, and I recommend the first one because like in this order, I think probability must be taught before we teach the average. So theoretically, mathematically, theoretically, probability theory precedes all the statistic theory, right? That's the basis, most fundamental foundation of statistics. So I thought chapter 1 should be probability. And this textbook follows that structure. But other textbooks usually talk about averages first because that is more common, more kind of easier to understand and easier to use. We use them more frequently in daily life. But I don't like them. So just to follow the structure that I believe is correct, I recommend this textbook. Okay. So anyhow, if you want to read textbooks, you can read these chapters. Okay, these are the overview of this chapter. Okay, let me start with the structure of probability. So in the end, I think the first chapter will be really easy to you, most of you, right? So the probability is exactly the probability you know, nothing special. It's not anything new. But what I want here is I'd like to set up some basic mathematical foundation, right? We'll be more rigorous. We will define the structure of probability so that we can unify the randomness structure. So there are different types of randomness, and we would like to describe them within the same framework. So there are a huge, literature about definition of probability. So I am going to tell you what's the basic fundamental definition of probability that statisticians and mathematicians agreed upon, right? So to think about that, I will start with a example sentence. So let's think about the simplest probability statement. When you toss a coin, the probability of heads is 50%, right? When you toss a coin, the probability of heads is 50%. There is no catch. This is exactly the sentence you know. Like this is the first example of this course. And we will analyze how to understand what are the components of this statement, probability statement. First, we have 50%. This is the probability, of course, but to describe this probability, you have to describe this. So it is probability 50%. Where is it from? That is this experiment, right? It is 50% is based on a coin toss. If you toss a dice, probability will be different, right? So you have to define the experiment that generates the randomness. And also heads is the probability. So we attach this probability to heads, right? So from an experiment, there must be some outcomes you are interested in, and you are attaching probability 50% to that outcome. That is heads in this example. The event of interest is heads, and we are putting 50% on that. That's how we describe probability. Exactly. So we have to define, we have to think about experiment, outcome, and sample space. Experiment is a process that generates a random outcome. Okay, right? That's pretty simple. And an outcome is a result from an experiment, right? So pretty obvious. And what's new is sample space. So we think about sample space. Sample space is the collection of all possible outcomes. So literally, we have to think about everything we can see, right? So, in some sense, like probability is mathematically a function. Then, when you think about a function, you have to think about its domain, its support. So, sample space is the domain. We can define probability on the possible outcomes, right? So that if you understand probability as a function, then sample space is the domain for that function. That's the basic idea, how we define probability mathematically. So in the coin toss example, which is pretty simple, there are only two possible outcomes, heads and tails. So the sample space is like the set of heads and tails, right? And think more about other examples, like rolling a dice. You get 6 different possible outcomes, so you have 6 elements in the sample space. And if you do an inspection, quality control inspection in a manufacturing process, defective or non-defective, when you inspect some manufactured product, you have to tell if it's defective or not. That's sample space. And when you play a game, you may win or lose or tie. So in a football game, basketball game, so there are 3. If you include tie as a possible outcome, there are 3 possible outcomes. Customer survey. If you design a survey like satisfied or not, there are 2 outcomes. But it depends on the question. If your question asks about a point out of like 10, from 0 to 10, then there can be 11 possible outcomes. So, and finally, income survey. If you ask about income can be any number, any non-negative number. Your income can be $0 or like $1 billion. Any number is possible. So in that case, you have to think about probability as a function from any non-negative number to probability, right? So then, that was what underlies probability. Then the probability is defined like this: the proportion of times that an event occurs when an experiment is repeated many times. Okay? So we are going to use this as the definition of probability. Actually, there are some competing alternative definitions in statistics, like Bayesian approach. So this definition is based on the frequentist approach. And there, as I said, there are alternative ways, like Bayesian approaches are the most famous alternatives, but like it's more like philosophical differences, and most of our analysis, at least undergraduate level, it does not matter if you just take this as the definition. So to make it simple, I will just stick to the frequentist approach. Okay. Anyhow, the point here is it's called the frequentist approach. So as the name tells, you have to repeat things and see the frequency, how many times a thing happened. So implicitly, this definition assumes that you are repeating an experiment, right? So that is kind of a hidden requirement to define a probability. But it makes sense. In many cases, our analysis is based on repeated observations. That's data. Data is the outcomes from the repeated experiments. So this is how we relate data to probability and statistics, right? So it's obvious. And then another famous term is sample size. Sample size is the number of repetitions, how many times you repeat an experiment. And usually, almost in any statistics, we call this n, denote this as alphabet n. Uppercase or lowercase, that may differ, but usually n stands for the sample size. Okay. So then, in general, one like universal statement or universal principle in any statistics is that the sample size should be large to make an accurate analysis. If the sample size is too small, your statistical analysis cannot be accurate, right? That's universal principle, but often it's not well recognized. Here is an example. So think about this coin toss. So I said the probability of heads is 50%. But how do you know that? How do you know that? I don't know. Actually, that statement, 50%, is not a statistical result. That is more like physics result under the assumption that heads and tails are equally likely. 50% is calculated mathematically from the assumption that heads and tails are equally likely outcomes. So then it should be 50%. For example, it rules out the probability that like your coin stands up. We do not allow that. Under those kind of assumptions, we get 50%. But now think about this. Okay, if you do not have that assumption, without knowing anything, how can you calculate that probability? You have to throw a coin repeatedly, right? So I simulated the experiment. For example, when you throw coin for the first time, it's heads. So then 100% probability it was heads. It was literally 100%. And then if you throw twice, then second one was tails, then probability of heads becomes 1 out of 2, which is 50% again, and then it's random. Actually, it's random. That means it doesn't need to be exactly 50%. It could be like, like say 70 something percent, like 50 something percent. It doesn't need to be, even if you throw like 1,000 times, it cannot be exactly 500 and 500. You may see 499 and 51 or slightly more deviate from that. But as the sample size increases, it will be accurately 50%. This is how statistics works, right? So coin toss is a simple example because you know the answer before doing the experiment. But in most cases, you don't know the actual answer. Like for example, similarly, what is the probability? What is the unemployment rate? That is kind of a probability if you classify people into employed and unemployed, and then how many people are unemployed. Then you don't know the answer, then you have to find many people and check if they are employed or not. So and in that analysis, what's important is large sample size. You have to repeat, you have to check many people, observe a lot of outcomes, and see, and then your probability will be more accurate. Okay, this is really broad and pretty straightforward and simple, easy definition of probability. So I will stop my first video here and I'll continue this discussion in the second video. See you there.